Hey everyone, welcome to week 4. This week, our focus would be on thinking and reasoning models. A lot of the amazing stuff that we see or hear these days are all or mostly powered by reasoning models because they are basically the most capable LLMs that are available today. So, our entire focus would be on learning about these models and we understand how they work. So, we'll start the week with an overview of reasoning models and we'll see different examples like OpenAI's O family and some other examples like DeepSeek R1. And then we'll talk about two main strategies to build reasoning models. One is inference time scaling, and another is training models with reasoning capability. So for inference time scaling, there are various methods. For instance, we go over chain of thought, self-consistency, sequential sampling, and different search strategies and verifiers. And after that, we'll switch to training reasoning models and different strategies like chain of thought training and methods like STAR. And we'll also talk about outcome reward modeling and process reward modeling, plus reinforcement learning. And after that, we'll go over approaches to an internalized search into the model and methods like meta, chain of thought. And finally, we'll explore deep research as an example of reasoning model and tool use. And finally, we have project 4, which is building a deep research-like system. So let's start the week. What is a reasoning model? The intuition is for complex prompts, a traditional LLM may not work too well. Those complex prompts, a lot of times, are better handled with multi-step logical answers. So when, for example, somebody asks about a difficult mathematical question, it's easier if we start a step-by-step answering and figuring out different parts until we reach the final solution, compared to just generating the final solution in the first run. And that's the intuition. So reasoning models are basically still an LLM, but they are capable of doing reasoning before they respond. So still there is an LLM and we have this prompt here, but instead of having a quick single pass to generate the response, first we have this reasoning step, which there are reasoning traces produced by the LLM. And it's typically multi-step reasoning, and it can be also multi-path exploration. So there could be, the model might explore different kinds of reasoning. And then once the reasoning is over, and once this kind of thinking is over, the model would start responding. So that's reasoning model, and we'll talk more about that. But let's see some examples. Most of the popular companies that are providing training LLMs and providing chatbot services, they are having their own reasoning models. For example, OpenAI has this O family, and there are a bunch of models that are reasoning models or advertised as reasoning or thinking models. Google's Gemini Pro, Grok 4, DeepSeek, and there are many other examples nowadays which are performing reasoning. So let's go and see some of these examples. This is ChatGPT, and by default, they are having this 4O model, which is not a reasoning model. And if we click here, there are a bunch of different models that we can choose from. And if you notice, some of these models are starting with O. For example, O3, O3 Pro, O4 Mini. These namings are a little bit not easy to understand for me. I don't know why they're naming it like this. But basically, anything that starts with O seems to be a reasoning model. And the ones that start with numbers like GPT-4o, and there are more models here, GPT 4.5, 4.1, these are not reasoning models. They may be able to show some reasoning ability as they respond, but they're not really specialized or trained for reasoning. However, these models like O3, it also they describe it as uses advanced reasoning. And this O3 Pro is best at reasoning. And this is more efficient version for reasoning, so it's fastest at advanced reasoning. And then they have O4 Mini High, great at coding. Again, there are some complexities here, but at the very high level, the ones that start with O are reasoning models. But now let's see what that means to reason or to think. Let me ask a question like count from 1 to 10 and then tell me how long it took. It's just a made up prompt. Let's see how it responds. All right, counting from 1 to 10, 1, 2, 3, 4, 5, 6, that took about 10 seconds in real time. So as you saw, it directly started to answer my prompt. There was no thinking or no reasoning behind it. And it's also outputting 10 seconds. We cannot say it's true because it was much faster. The model printed all this in probably less than a second. But still, it's saying that 10 seconds, which is not correct. But part of it is because also there is some ambiguity in my prompt. It's not really clear if we want the model to output the time it took to print those, or basically we want the model to print the time that generally if somebody counts, it would take them. But regardless, this is what it outputted. Now let's switch to a reasoning model. I'm going to choose O4 Mini just because it's faster. For a lot of like day-to-day tasks and questions that are more complex, I typically default to O3, and that's usually enough. But if the task is very complex and I require more reliable response, O3 Pro is usually better, but it takes very long for now, so I don't like to wait that long. And O4 Mini, I don't use it often, but again, if there are tasks that we really don't want to wait, we can just use it. Now, I want to use the exact same prompt and switch to O4 Mini so we can compare. Let me create a new chat. So you see it's thinking. And then here are some reasonings that are happening. Basically, it says, okay, so the user wants me to do this. Okay, the user wants me, and then it's counting. So there was a thought for 9 seconds. And this is what reasoning models are. They think, and then they reason based on my ask or request. And once they're over, once this 9 second is over, then they may start generating the final response. And in this case, it's counting for me from 1 to 10. And what is interesting is that it says I ran a quick loop to count from 1 to 10, and it took about 0.00012 seconds. Now, this seems to be more convincing to me because this is how long it took for the model to really print these. So it seems to be working better than a single pass 4O model. Now, if I click here, we would see the thought process. Basically, this starts by saying, okay, so the user wants me to count from 1 to 10 and tell me how long it took. The challenge here is that I'm ChatGPT. I cannot track real time. So then it decides to write a code and then capture the time. And then from here, it finds the time. And then finally, once everything is over, it's ready to answer my question, which is counting and then printing the time it took. Now, one thing to note is that OpenAI is not showing the actual reasoning traces. So it's not exactly what the model probably have been thinking. It's a little bit different or rewarded. I don't know how they are rewarding or coming up with this explanation or thoughts, but it seems that they're not really showing the actual reasoning traces, actual tokens that the model is generating as part of its thought process or reasoning. So before I switch to the other example, let me also use the exact same prompt, but use a more advanced model like O3 and see if there is any difference. Now, my expectation is that it would take longer because it's more capable model and it may decide to think more and try different strategies. So let's see if that's really the case. All right, it seems it's taking longer and there was a little bit of more thinking, but let's see what it outputs. Again, it's just thinking more and reasoning more over how to properly answer my prompt. And again, that's why there are more efficient models out there like O4 in case you don't want to wait too long. For example, here I may run out of patience for, especially for simpler questions. If it doesn't really require reasoning, it's an overkill to switch to more capable reasoning models. So see, it's still thinking, and then now it wrote the code, and probably it's going to answer now. All right. So it started to answer, and then it says the time is this, which is very similar to what O4 outputted. But now the difference is that it took 1 minute for this model to think and reason. And that means that the model generated more tokens, and therefore it was more expensive for the model to handle this prompt, just because it took more time for the model to think and generate tokens. So that's reasoning models. Again, different companies are having their own reasoning models. This is Gemini from Google. By default, they have this 2.5 Flash, and then there is this Reasoning Math and Code 2.5 Pro. So this is basically their reasoning model. And then again, similar for Claude by Anthropic. So here they have Cloud Opus 4, and then that's a hybrid kind of reasoning model too. So now there are lots of different reasoning models. If we come to this leaderboard that we saw in week 1, which has this ranking of all different models, you would see the best models out there are reasoning models. And that's because they are more capable. If we put this reasoning step before the final response, and we basically let the model to think or generate more tokens and reason and try different solutions, they typically work better and they are more powerful. For example, the first rank, which is Gemini 2.5 Pro, that's the highly ranked, the best model overall, and it's a reasoning model. Also, the next one is O3, which is also a reasoning model. Now, this one, ChatGPT 4o, is ranked 3rd, and it's not a reasoning model. So it's very impressive that it's competing with many other reasoning models here, and it's doing better. Then we have Grok 4, and Grok 4 by XAI, it's also a tie. It's ranked 3rd. And then this model is also a reasoning model. I went to their documentation here, and then as they are talking about the context window and the details of it and features, they say that it does function calling, it supports structure outputs, and also it has reasoning feature. So it's a reasoning model. Now, the next thing I want to show here, let's go to the leaderboard. So that's Grok. GPT 4.5, that's not a reasoning model. So it's impressive. And it's tie, again, it's ranked 3. So 4.5, 4.0, and Grok 4 all are tied. And Grok 4 is reasoning, but these two are not. Now, this one is interesting. This is Kimi K2, and this is a company called Moonshot, released it recently. And what is interesting about this model is that while the company behind it is not as big as companies like Google or OpenAI, probably, but this model ranked 5 in such a short time. So it's very impressive. It's doing very good. And also, it's not a reasoning model. So this is their website, Kimi K2 Open Agentic Intelligence. And they're saying that non-thinking models. So this model is also super impressive. And if you look at the benchmarks and comparisons at different tasks like agentic and coding, the model is doing very good compared to some other like OpenAI and Anthropic models. And similarly for tool use, it's doing quite good on different benchmarks, and math, it's doing reasonably good. So, and also they published a technical report recently. So it should be a very interesting read with a lot of details. Now, again, one more thing I wanted to share is that another interesting thing with this Kimi 2 is its license. It's modified MIT. I haven't read the details of modified MIT, but in general, it is giving permission to use to some extent, I assume. So basically, it's an open source model which we can use to build some applications on top of it. Then we have Claude Opus 4, and after that is DeepSeek. DeepSeek is also a Chinese company. And when this model was released, it was the first model that was open source, and it was showing the actual reasoning traces. And also the technical report was very detailed. So this was a big deal because also the license was MIT, meaning that basically MIT license says that users can use, copy, modify, merge, publish, distribute, sub-license. Basically, they can do whatever they want with the model and the code, which is amazing because it allows people, startups to start from this very powerful model, which is very competitive. It's ranked 6 among all the best labs and companies in the world. And the startups can just start from this model and build applications on top of it and commercialize it. So, and DeepSeek R1, basically, again, they published their paper. We go to some details of it this week, but they have this paper and they're saying exactly it's, many pages. They're saying how they are building and training this reasoning model. So it's good to read this. And finally, I want to show the same example, but here in hyperbolic, I selected DeepSeek R1. And I want to use the same prompt that we saw here and see how hyperbolic would respond. So let me paste this here. And also I'm going to increase these max tokens because now the model is thinking and reasoning. So there's a lot of tokens involved and the model needs to generate before it reaches the final answer. So let me just change it to 10,000. So we let the model basically think quite a bit and reason quite a bit. And now let me send this. Maybe I have to refresh. All right, so now it says it's reasoning. And if I click here, basically it's showing the actual reasoning traces, which is awesome. These are the exact tokens that the model is generating during its reasoning process. It says we'll generate the numbers from 1 to 10 without delay and then calculate the time taken. Alternatively, basically now it's considering a different solution. We can use a simulated time. For example, we can say we counted at a rate of 1 number per second. Let me reread. And then again, it says, I think the user expects the time taken to count. Counting from this, because I'm a fast computer. Basically, at this point, it's getting into the ambiguity that is in my prompt. Because as I mentioned, there is some ambiguity in the prompt in a sense that what does it mean? How long? Is it for somebody if they want to, a real human if they want to count, or for computer? So it's getting into that part. And then it says, alternatively, we can measure the time text to generate the response string. However, the time, so it's very interesting and it seems it's in the right direction. It's thinking about the right things and try to disambiguate certain ambiguities. Then finally here it says, let's do a start time. Let's go here and do this. And finally it decides to build a string. So there is some code here, but note the assistant is running in a sandbox. I don't know, it may actually run out of the 9,000 tokens, but let's see. Let's decide. Again, as you can see, there are lots of tokens involved and it's very, very expensive because in order to generate these tokens, there needs to be some infrastructure and GPUs. So it's costly. The longer these reasoning traces, the more expensive it would be to serve users' requests. So there should be some balance. But again, this is just a demo, an example. Here it's deciding to use the time module, Python's time module, and date time. So, okay. And finally, it's over and says counting from 1 to 10. It's actually counting. And then it says the time taken approximately this. And finally, it says, as an AI, I process tasks nearly instantly, no physical counting required. So I think I would rate it the best probably compared to OpenAI ones because it's exactly thinking about the right things. It disambiguates my prompt. It shows, it counts then it shows some reasonable number. And also it mentions something here that, hey, I can just print this instantly. So, and what is even more interesting is that we are seeing the actual reasoning traces. We are not seeing a part of a rephrased or reworded version of them. So DeepSeek is also very capable, and a lot of companies might have decided to use it or fine-tune on top of it a model that is less biased, let's say, in certain aspects. But it's a very good starting point. At least at the time, it was a very good starting point. And then the rest of the models, you can just go through this list. I wanted to just get into these DeepSeek, Kimi K2, and closed models here. So this is reasoning models. We saw various examples, and we saw how it works, and we learned about the high-level intuition of what is a reasoning model, why it is needed. But let's get into the actual approaches that we can build reasoning models. Hey. We'll continue our discussion, and we'll now learn how can we really build these reasoning models. And there are different approaches and different techniques, but they can be categorized in two big buckets. One bucket is through inference time scaling. And basically the idea of all these approaches are that we allow the model to reason by giving it more compute at inference time. So basically during the text generation, we just allow it to generate more text and more tokens with some mechanism or some algorithm. So this way, we are not really touching the LLM's parameters, or we are not training it. Everything is going to be frozen. The same LLM, we are going to use it, and we are going to just apply some algorithm or some additions at inference time. So the model becomes capable of reasoning. The other bucket is training with reasoning. And all these different ideas, which are also very powerful, are taking a different approach. They are scaling the training compute. They are spending more time to continue training the LLM so that the LLM becomes capable of reasoning. And we'll go over all these different approaches in the future lectures. So for now, let's focus on inference time scaling. And again, as I mentioned, the idea of inference time scaling is to teach the model or allow the model to reason through giving it more inference time compute. And the first approach that it's also the simplest approach, is relying on the prompt engineering technique that we covered previously. And in particular, chain of thought prompting is very powerful for this use case. For example, let's say without any chain of thought prompting, if we ask a model a question like a math question, like there are 3 red bags with 5 apples each and 2 blue bags with 7 apples each, how many apples are there in total? For something like this, if there is no chain of thought prompting, the LLM, at least the LLM in early days, might produce something like the final answer, 20. There is no basically, the LLM is not expected to produce a multi-step reasoning and how it reaches to 20. It might directly output 20 or something like the answer is 20. Now, with few-shot chain of thought prompting technique, we can add an example to the context, in the context of the model or in its prompt, and we can show how to answer for similar questions. For example, we have a question here which has a similar type and a style to our actual question. So we have here, there are 2 boxes with 3 balls each. How many balls are there? 2 times 3 equals 6. So, comma, 6 dot. So this is the example that we are showing it. And now we say, now solve this, and then here is the real question that we have. Basically, it's just a prompting technique. We are showing it one example with the reasoning traces. And in this case, the reasoning is very simple, but it can be multiple examples with more like multi-step reasonings and also textual description in each reasoning trace. But this is just a simple example. Now, in this case, the LLM is very likely to produce the final output, including the steps like intermediate steps as it reasons, because it wants to follow the provided example. For example, in this case, it may output something like 3 times 5 equal 15, 2 times 7 equals 14, 15 plus 14 equal 29. And then next, for the final answer, it would exactly follow what we were showing it. So, comma, final answer dot. And here it says so, comma, 29 dot. And this can be very powerful and important because this way we can easily parse the output if it's following a certain format. We can easily parse the output and then only extract the final answer. So we don't necessarily, or we don't always need all these intermediate steps. In many cases, all we want is the final answer. Also, when we want to evaluate LLMs on, let's say, math problems, we typically want to somehow extract the final answer. So knowing that the model would follow a certain format, like always once the reasoning ends, it has dot, so, comma, final answer dot, it would become very easy to extract the final answer and compare it with the correct answer, let's say, to evaluate the LLM. Now, just to see this, let's try this Llama 3.2 3 billion. And then I have the same question here that we had. Let's see if it would output the final answer or it would also do some reasoning. What I expect, before I press this, what I expect is that there might be some reasonings involved because these models are more advanced and trained later in different data sets. And many of the data examples in its data set might have reasoning traces and multi-step logics. So these models might still generate some intermediate steps to solve these problems. But let's see. Okay, so it's obviously failing. And it says there are 3 red bags with 5 apples, which is not what I really wanted. Now, let's now copy paste this and see if it makes any difference. Again, I intentionally selected this 3 billion model so it's a smaller model, it's less capable, so that we can show the difference when we show examples. Because if we choose more powerful models like 8 billion or 70 billion models, they are already very capable and they know how to reason without even asking it to reason or showing it some examples. But in this case, this model failed. Now let me print this. This is the exact same question that we had, but now we are showing it one example. Let's see if it works or not. I don't know what's happening. Let me refresh this and paste again. I don't know, it even got worse. Oh, maybe it's because of this. All right. Okay, great. So now it's doing better. It's not exactly following the example that I showed it, but at least now it's doing some calculations. And then it's getting into the final answer and says, therefore, there are 29 apples in total. So basically, this way, we can force or push the model to reason, especially less capable models. Now, back here, we saw few-shot COT prompting by showing some examples, but there is also zero-shot COT prompting, which we don't have to show any examples and still ask the model or push the model to reason and think. And basically, the idea is coming from this paper. Large language models are zero-shot reasoners. And what they are showing, they have a very comprehensive and detailed evaluation of different techniques. And what they're saying is that all we need to do for zero-shot chain of thought prompting is to add let's think step by step to our prompt. So this way, we are not showing the model examples on how to reason or how to think, but we are just asking it to do so. And it can work in practice because these models have learned from internet data that a lot of times when there are things like let's think a step by step, or here is a step by step explanation. So there are a lot of similar things on internet data. And the model already knows that when such things are there, usually the response is more detailed with intermediate steps. And because of that, it would just work. The model would, for example, for this example, if we do zero shot, basically we just show the answer. It would output 8, which is incorrect. If we do few shot, meaning that we show one example and then we ask question, still it's going to fail. With few shot COT, it's going to work, meaning that it's not only few shot, but we are also showing how to reason by including the details in the answer and intermediate steps. But there's also here showing that we don't have to show examples here. We can apply zero shot COT. And that's only appending let's think step by step. And in this case, the model would still get it right and answer it correctly. So again, there is a lot of details and evaluations, which is very nice to read. But the idea is very simple of zero-shot COT prompting. We just append, let's think step by step to the prompts. And this way we push the model to reason. So this is prompting and chain of thought prompting. There is a different way we can visualize this and think of this COT prompting. Basically, when we don't have a COT, we are going from the input to output directly. So this is the user's prompt, and this is the model's final answer. When we add COT, let's say through prompting, this is going to change it like this. Now the input is going to produce some thoughts, and these are intermediate thoughts. Thought 1, thought 2, thought n. And then finally, after thought n, the model would just wrap it up and generate its final answer. So these are all the intermediate reasons or steps. For example, in this example, 3 times 5 equal 15 can be thought 1. 2 times 7 equal 14 is thought 2, and so on. And then the final answer is 29. Again, this example is simple. In practice, each thought might have a textual description as well. For example, it can start with something like, to calculate this, we have to add this plus that, and then some numbers. So the reason that I'm showing this visualization, because as we switch to other inference time scaling techniques, it's easier this way to compare them and understand how they are improving upon each other. So that's COT prompting. Next, we are going to switch to a different technique. So the second approach is called self-consistency. And it's also a very powerful way of scaling inference time compute. It has also different terminologies. I've seen different terms being used. For example, in some articles or blogs, it's called parallel sampling. It's also called best of n sampling a lot in evaluations. So all these are referring to the same thing, and the idea is very simple. The idea is instead of spending our compute budget on reasoning traces or basically generating more intermediate steps, instead let's sample n times from the LLM, and then we pick the best one. So basically the idea is when the prompt comes to the LLM, we simultaneously start, let's say, 4 different generations. And we apply our sampling method, generate 4 full responses, and then pick the best one. And basically we have full control over our spending budget, compute budget, because depending on how much we want to spend to scale our inference, we can adjust this n, like n refers to the number of generations. Here it's 4. Basically, the more we increase the n, we are spending more tokens at inference time. But instead, we may get better responses, better overall response. And the other way we can think of or visualize this is now, instead of going from input to output directly, we can generate 3 responses in parallel and then identify the best one, and then pass this one as the final output. We'll talk about how we can really pick the best one. How can we measure what is the best response? We'll talk more about that. But again, for now, let's assume that we have some way to pick the best response. So this is self-consistency or parallel sampling because we are sampling in parallel. It's also called best of n because at the end, we just pick the best answer out of the n generations. Now, there was this paper called Self-Consistency Improves Chain of Thought Reasoning in Language Models, published by Google. And the idea is very simple. What they're suggesting is, again, the paper is very detailed and nice to read. But the idea that they are proposing is that let's combine self-consistency with chain of thought. So now, instead of having one branch of chain of thought or having just self-consistency without chain of thought, which is like this, we basically combine these two to get something like this. Basically, now each branch by its own has a chain of thought integrated into it. And in total, we have n parallel generations. So after each branch is over with its reasoning and generate the final response, then we can apply our algorithm to pick the best response and then show it as the final output. And again, you can read the paper. It has a lot of evaluations, but basically it's saying that this way it just keeps doing better and better, especially as they increase the number of samples or sampled reasoning path. You can see in certain domains and certain models, it's just keep doing better and better as they scale. Here is the accuracy. So the accuracy, for example, here keeps going up. And here you can see the colors. Basically, it's greedy decode. It's just one generation, which is always fixed, no matter what is the reasoning path. And then they have self-consistency, which is blue. So you can see in all these different domains, in different benchmarks, this blue is just keep getting better and better. The accuracy keeps going up. And that's because they're just sampling more generations and then pick the best one out of them. So again, there are lots of evaluations and interesting details about it. But the idea is simple. They combine self-consistency with COT. Now, the main question we need to still answer is how we really pick the best response. So let's talk more about that. There are two main ways to pick the best response. One is majority voting, and the other is using a reward model. And the names are obvious, so probably you can guess what each of these approaches are doing. So we'll go briefly over them. Basically, the idea behind majority voting is that once we have these n generations from the model, if they are following a certain format and it has a certain, basically the prompt is in a certain domain, like mathematical questions, we can simply compare them and pick one of them that the majority agree about their final response. For example, here we have 4 generations. The first generation has some chain of thought, intermediate steps, and then it says, so 29. So the first response, it believes that the final answer is 29. Then we have the second answer, which do some, again, reasoning, and then it believes that the final answer is 28. Now, the advantage of having multiple steps is that at this point, basically, we are confused because one generation is saying 29, another is saying 28. So we just see what other generations are saying. Now, the third generation is saying 29. The fourth generation is also saying 29, regardless of how they are reasoning or what are the intermediate steps. So by just looking at their final answer, we are seeing that 3 out of 4 responses are believing that this prompt has a final answer of 29, and one of them is saying 28. So we just run some voting mechanism and we use the majority of the votes to use them as the final answer. And here it's 29, so we can randomly pick one of the answers that believe the final answer is 29 and then show it to the user. So that's majority voting, and it's very simple. But the problem is it only works in certain domains. For example, in mathematics, it works well because we can easily parse the output if it's following a certain format. We parse the final output, figure out what is the final response or final number that the model is predicting, and then we do majority voting. But imagine a different domain. For example, if it's writing, it's a writing task. Basically, the prompt says, "Hey, write an article or write a blog regarding this topic." In those cases, there is not really a correct or incorrect answer, and comparing them is more subjective, and it requires real humans to say which answer is better and which answer is worse. We cannot have really some automatic voting mechanism to compare them. Because all of those generations, for instance, for writing tasks, they are probably correct and relevant. It's just certain details that one of them might be doing better than the other. So for those domains, the method that we can use to pick the best response is to use a reward model. And that's what we have here. We saw reward modeling in previous lectures, in previous weeks. And then we saw that how these models are trained and used to post-train LLM. Let's just briefly review them. A reward model is basically trained on pairs of prompt and responses. And it's capable of producing the score, that how this response is scored for that particular prompt. And the way that these reward models are being trained is generally we manually collect data and real humans annotate them, score them. So let's say we have thousands of prompts, and for each prompt we have lots of different answers. So some humans sit and look at these answers and score them. So basically we have now this annotated data set of pairs of prompt and response, and their corresponding score, which reflects a human's preference for that pair. And this reward model architecture, it can be very similar to LLM. It can be just a decoder-only transformer, and then it looks at the input, which is a pair of prompt and response, and then it produces some number or some score. So after this reward model is trained, we can just use it to pick the best response in our setup at inference time scaling. So whatever the question is, we just generate, let's say here, 5 responses. And each response is passed to this reward model along with the original prompt. And then the reward model score each pair. So we would have 5 scores here. And then we look at the scores, we pick the highest score, and then we show that answer as the final answer to the user. So basically, this setup allows us to expand to different domains. So it could be writing, it could be any other tasks. As long as we have a reward model that is trained on similar data, we can just use it to pick the best response. All right, we talked about 2 very popular approaches for inference time scaling. One is COT and one is self-consistency. And these 2 are often combined. And a lot of early LLMs capable of reasoning were just using these 2 approaches to basically generate better responses. Now, the next method I want to talk about is tree of thoughts. Basically, if we look at no COT, COT, and COT plus self-consistency, you can think of this decoding, basically the text generation, it's becoming more like a search problem. Basically, we have this input and output, and we can easily control like the number of intermediate steps, and also we can add more branches here. And for each of these thoughts, we can also add more branches. We don't have to necessarily just sample once. Again, we are not doing it here, but it's just the look of it is becoming more like a search problem. And basically, tree of thoughts is built based on that. And then after tree of thoughts, there are lots of other different methods that are treating this decoding problem as a search problem. So the idea behind tree of thoughts is why not we form a tree instead of having this fixed set of workflows. We can start from the input. We can generate some intermediate thoughts. Then we can, let's say, somehow score them. We pick the best ones, and we continue this generation process. Basically, now from this thought, we can continue the generation and add 1 more thought. From this thought, we can generate 4 more thoughts because it's dark green, meaning that it has a high potential to reach to the good answer. And again, from here, we can generate 4 more thoughts in parallel, and these two are very off. So, and also this is not too good. So we would discard this. And this is again dark green. So it's a real good continuation or intermediate step. So we would just expand on that. So basically the idea is just to apply some more complex search algorithm and expand this tree as we move forward dynamically. And then finally, the best path with the highest score, let's say, it would form the final output. So basically, it's not too different, at least this tree of thoughts, from just COT with self-consistency. It's more focused on efficiency, because basically what we can do is we can just generate, depending on what is our compute budget, we can generate more samples in COTs and self-consistency. We can have 10 branches. And from their paper, it can be shown that there are lots of papers that are proving that if we spend enough compute budget with this approach, we would get really good outputs. The main advantage of tree of thoughts is the pruning that is happening. So it's more efficient than this. Basically, we are not, as soon as we believe that a path does not have a potential to reach a good response, we would discard it. For example, here, let's say the first thought that we have in this third branch, at this point we evaluate and we see it's not a good idea. So we are not really continuing this branch. Whereas in COT self-consistency, if we look at the third branch, we are not really terminating it. We are just going all the way through, let it generate intermediate steps, and then finally we look at it and see it's not good. So tree of thoughts is more focused on efficiency. And I don't have the paper open, but it's just tree of thoughts. I think if you search the Google, it would just show up. So, and again, there are a lot more approaches after tree of thoughts, and they all are treating this problem as a search problem. And then there was this paper called Scaling LLM Test Time Compute Optimally, and it's published by DeepMind in 2024. And it's a great paper. I strongly encourage everyone to take a look at this paper. It just goes over how inference time scaling helps and what are different methods and a lot of evaluations, and how increasing the generation budget can improve the accuracy of in certain domains like math. For example, this red is basically showing parallel sampling, and then applying different methods like majority voting or best of n weighted and so on. Again, you can read the details. But what I want to show here is that they are also comparing different algorithms. So best of n, we already saw. We just sample n answers. We pick the best one. But if you treat this problem as a search problem, there are more innovative, more efficient, and more smarter way to expand this tree. For example, we can apply something like beam search. And at each step, we generate a fixed number of path, and then we keep top k. In this case, I think they're keeping top 2 best path. And they just keep doing this. And finally, once we have the final answer, they would just show the highest, the best, basically the best path with the highest score. And then they're also having this look-ahead search. I don't know if this paper was, basically this look-ahead search, it was proposed in some paper. I don't know if it's this paper or it was another paper. But basically the idea of this is, again, a search problem. They roll out, so basically from each thought, they continue it for a few more steps. And then they look at if it gets somewhere reasonable. If not, they would just get back to this part. Again, there are more details to it, but all these are different ways of handling this text generation or text decoding as a search problem. So, yeah, I think this is an amazing paper. I really suggest you take a look if you haven't. So these are, we went over a couple of different approaches like parallel sampling, different ways of searching, and tree of thoughts, and we saw more advanced searchings. But all these are basically spending our compute budget in parallel. For example, here we have like 3 parallel paths. The other approach that we have, it's called sequential sampling. And the idea here is that we sequentially try to spend our compute budget. And what that means is that whatever the prompt is, it comes to the LLM. We can also include chain of thought prompting, so it includes reasonings. And then we get the response. And now we can pass the response and the prompt to the same LLM, or it could be a different LLM, but let's say it's the same LLM. And we ask it to revise or improve the response. And we have a fixed number of generations. In this example, k is equal to 2. So we are sequentially sampling and keep revising and improving the answer. And then the final answer, the final output of the LLM would be the final answer. So basically, we have a very simple pseudocode here. Basically, for this fixed k times, we would sequentially sample from these LLMs. And then the output of each step would go as the input to the next step. This is also another way that we can scale our inference time and generate more tokens and basically let the LLM to think more or reason more and then come up with the final answer. Before I wrap up the inference time scaling, one thing I want to point out is that many of these approaches can be combined. And I believe there were certain studies that were suggesting that earlier reasoning models by OpenAI were doing something similar. They were using sequential sampling, and at the same time, they were also doing parallel sampling. So again, a lot of these can be combined. We can have sequential sampling, and for each sequential sampling, we can have a parallel sampling going on. So instead of just directly generating this response, we can have multiple responses. Then we can use our reward model to pick the best response, and then pass that best response along with the prompt and continue this sequential sampling process. Also, there are some other papers that are suggesting that sequential sampling is better for easier or medium questions, like basically questions with easy or medium difficulty. And parallel sampling might be better for questions, more complex questions with more difficulty. And the reason for that is intuitively is because for simple and like easy and medium difficulty questions, usually the LLM can get it right or can be in the right direction in the first pass. So the first response is reliable enough, and we just need to continue refining it. Whereas in complex problems or problems with very high difficulty, it's very likely that the LLM won't be in the right direction in its first try. So it was observed that if we have multiple parallel branches and the model think in parallel, so it may try different ideas, and few of them may be maybe in the right direction. So again, there are lots of different papers, and they are evaluating these different methods in different way. They can be combined, and in practice, they are combined. But the core idea behind inference time scaling is just to spend more time generating tokens. Let me see here. Is basically spending more time generating more tokens at inference time and not touching the original LLM and not touching its weights. I didn't cover Monte Carlo search. It's one of a different way to run some search algorithm on that tree. Basically, we saw different examples, but Monte Carlo search is also another example to run search on the tree when we are decoding. But again, this list is not comprehensive. It's just some very popular methods that were used in earlier days or are very powerful. But there are a lot of other examples for inference time scaling. Now, with that, we are going to switch to the training with reasoning capability. And that's what we are going to focus on next. Hey, let's continue learning about different ways to build reasoning models. In the last video, we saw various techniques at inference time where we can use to improve the quality of the results. We saw, for instance, COT prompting, which pushes the model to reason before generating the final answer. And therefore, the model generates intermediate steps, and after those, it would show the final answer. We also saw various techniques to let the model to explore different ideas and think in different directions. For example, we saw in self-consistency, we can force the model to simultaneously explore n different generations, or in other words, n different thinking or directions, and then we pick the best one. We then switch to more complex ways of building a tree and searching over it. And basically all of these ideas basically allowing the model to think in different directions and prune directions as soon as they seem to be not leading to the right result or is not optimal, and continue branches that look promising. And there are lots of different search algorithms, but at the end of the day, it's a search problem. It's basically we form a tree, we let the model to think in different ways, different directions, generate different thoughts simultaneously. And then as we are forming this tree, we keep continuing some branches, pruning some branches until we reach to some leaf nodes, and eventually we pick the best leaf node, which basically shows a certain reasoning trajectory of the model. But all of these methods are basically techniques at inference time. We are just trading off compute at inference time, so we get better quality or better responses. And we are not really touching the parameters of the model. The LLM itself is just the original LLM that were trained. So it's not really capable of generating thoughts or reasons or think in parallel or anything like that. For all of those, we are using some manual techniques or algorithms at runtime, at inference time. Now, the other category which we are going to focus on in this video is training with reasoning models. Many of these techniques have an equivalent on the training side. Basically, instead of, for instance, pushing the model to generate reasons, intermediate steps, for instance, COT prompting, we can train a model so it learns how to generate chain of thoughts. And these approaches generally seem to be more effective. And again, there is a trade-off. Both of these can be also combined. For instance, we can combine still search or sequential sampling with some of these training methods. And it works quite well. And in practice, many of the best reasoning models out there, in fact, are combining some of these methods. But let's just start focusing on different techniques to actually train the LLM to gain that sort of capability. So the first thing that we want to discuss is training with COT data. We saw how we can use COT prompting previously for the model to generate intermediate steps. But the model itself, again, is not capable of doing that. So here, the idea is, what if we continue training the LLM and providing it with COT data? Basically, we provide it with data which has prompt, and then instead of the final answer, it has the intermediate steps followed by the final answer. So this way, the hope is that after training on this data, we would get a new LLM which has these tuned weights compared to this. It has the same architecture, but just different weights. But now this model is inherently capable of producing thoughts or producing intermediate steps. For example, when we ask a math questions, this is expected to not directly answer the final answer, but it produces the intermediate steps and then final answer. And this way, basically, the model is going to be more accurate because in some sense, the idea is the same. It's going to break the task into smaller steps, so it becomes more easy for the model to solve it. And again, we are trading off compute here because no matter we are using COT at inference time, using prompting, or COT and we train a model, this new LLM would still be a model that generates more tokens compared to this LLM. Because now this model is generating intermediate steps. So what that means is that we are spending more tokens in order to get the final answer. And so we are trading off compute for better or higher accuracy. Now, training with COT data, there was this paper, Self-Taught Reasoner, or a STAR, that was published in 2022, and it's a very powerful technique. Initially, this technique was used to train a model with COT data, but then later, the whole idea were used for other advancements and different ways of improving LLMs. It's more like a mechanism to generate some data. So let's see what the idea is. Basically, I'm not going through the paper, but basically this is the overview of their method. So what they're saying is that we have this language model or LLM, and it's not initially capable of generating intermediate steps. So what we can do is first we can try prompting technique, COT prompting, which we saw previously. And we pass certain question and we ask the model and we show some examples to it, let's say, since it's COT prompting, hoping that this LLM would generate rational and the answer for this particular question. So once we see this, we can easily identify whether the answer is correct or not. Because let's say if we are collecting or generating this data in a certain domain like math, it's very easy to parse this output and see if it matches the ground truth or not. If the final answer is correct, now we have some rational or intermediate steps. Now, this, along with the original question, would form one example of our training data. And once we have a bunch of examples of like in this format for our training data, now we can start fine-tuning this LLM on this data. So let me go back to our lecture. Basically, the main question and the main thing that the STAR method is solving is how to collect COT data. Because once we have the COT data, it becomes easy to just continue training the LLM on it. And the idea is iterative. As we saw, we first use few-shot prompting to get a model that can generate rationals. We use those rationals to get a data set. We use this data set now to fine-tune this LLM. And then after we get this LLM, we use more questions to generate more rationals. And again, we would use the new rational answer pairs to iteratively fine-tune this again. So basically, we just bootstrapping the model. The LLM keeps getting better at generating intermediate steps. And there are more details into the paper. You can read it if you are interested. For example, they say that if at some point some of the outputs has the wrong answer, we can determine that, and we can give a hint to the model, hoping that with this hint, the model would now be able to generate the answer correctly. And if the answer is correctly, we would also include those in our training data for the next round of training. So that's the key idea, to collect COT data. And once we have the COT data, basically the next step is to introduce special tokens and then train the LLM. And what do we mean by a special token? What we mean is that now we have two components in the output. One is the rational or the intermediate steps, and one is the final answer. In order to distinguish between these two, we can define a particular tag or a special token so that we can specify when these rationals are being started and ended. For example, people use things like this think tag or a scratchpad tag and so on. I think a STAR paper is probably using a scratchpad. Yes, they're using a scratchpad. So basically for a question like this, first the output generates this scratch, meaning that it's in the thinking process. It's in the process of reasoning and creating these intermediate steps. It just keeps generating and generating and generating. And once it's confident about the final answer, it would close this tag, this thinking process using this special token. And then after that, it's when it produces the final response. So basically, this is the format of the data that we create to train our LLM. And most reasoning models, they do have a special tokens for thinking. They're just naming it differently. For example, here, if we choose a reasoning model in Tick Tokenizer, I don't know if they're having any, because most reasoning models are closed source except, all right, so they have DeepSeek R1. And we saw that this is basically just showing how, for a sentence, it's being tokenized into a sequence of IDs. For example, hi, how are you becomes like this, hi, how are you? And each of them gets replaced by their IDs in the vocabulary. Now, if we put something inside this, like I am start or, hi, we would see that this becomes one token. Hi, since it's a meaningful term, it becomes its own token. And then this becomes its own token. So we have 3 tokens here. And then these are the IDs. For this opening, it has 30. And then when we are closing it, it has a different ID, 32. Now, let's see if they are using a scratchpad. No. What they're using is this think. Basically, if we have this think, it's just 1 token. And this is the token ID. And I think this would be also another token with this ID. So it is 128,798. And when I add this, it becomes 799. So these 2 tokens become those special tokens that they're using to basically build their data and train this model using those special tokens. So when the model wants to generate the rationals, they can just generate all those intermediate steps within these special tokens. So, and once we define this, we just add this to our tokenizer and our vocabulary, and we make sure that our collected data set is following this format. We apply this template to it. So everything that is a rational goes inside these tags, and everything which is the final answer, they are outside of these tags. And once we have this data, the rest is very simple. We just continue training the LLM on this new data, in a very similar way that we initially trained the LLM. Now, by doing this, the LLM would adjust its parameters so it adapt to this new distribution of inputs, meaning that now the LLM would learn to generate these think or a scratchpad special tokens, think inside them, and generate reasons and intermediate steps. And then once it's confident about the answer, it would close this tag and generate the final answer. So after training, if we ask a model a prompt, something like this, the output would sound something like this. Or sometimes this answer tag might be skipped because we can assume anything that is outside of the think tags or just the final answer. But we can also include them for clarity or having a structured output. But we would get something like this after the training. And this is perfect because now basically by following this star to collect data, iteratively fine-tune this LLM to generate rationals, we would end up with a model capable of doing reasoning. So we no longer need to apply any prompting technique at inference time. The model is just capable of performing reasoning. Now, many of the current models, even if they're not reasoning models, are typically trained on data with reasoning traces. For example, if we go to ChatGPT and we just keep their 4.0, which is not a reasoning model really, but still we ask a question like, things like how long it takes to go to moon from San Francisco by walk. I believe it may use some sort of intermediate steps before concluding or before coming up with the final answer. Let me enter this. So this is exactly what is happening, right? So all these are those intermediate steps. Instead of just outputting the final answer, which says 27 years, it would come up with first clarification, some key assumptions, distance to moon, and these are necessary. Without these, the model would have a more difficult time to generate the correct answer. Basically, these are necessary. This is just, the model is cheating by generating these intermediate steps since they are simpler tasks and the model already knows them, so that at some point, then they can come up with the final answer. And even for the calculations, it's not directly calculating it. It's calculating it in 3 steps. So all I wanted to say is that even models that are not advertised as reasoning, they've been trained on lots of data sets, lots of examples in their data set. And those examples, a lot of them nowadays are having these chain of thought intermediate steps within them. So the model learns to generate these steps. So that's the first approach, training with COT. So we get a model that can really reason. So now let's move to the next technique. All right, the next technique is RL with reward model. But let's understand what that means. We saw that most of these methods for training a model with reasoning capability, they kind of have a similar equivalent in the inference time scaling. For example, we saw that a star basically tries to train a model with COT capability, and its equivalent inference time method is COT prompting, which we just prompt the model to generate chain of thoughts. Now, this RL with ORM, PRM is kind of equivalent to self-consistency, which we saw at inference time. So let's just briefly go there and take a look. Basically, the idea of self-consistency was that we have this model and we just generate multiple outputs from this LLM for the same prompt, and then we pick the best one. Now, its equivalent in the training is that why not we continue fine-tuning this LLM with certain methods. Let's say we use reinforcement learning and we use a reward model. We continue training this so that it becomes more likely that the model generate this better response in the first try. So basically, we just continue training the LLM based on this kind of data that we can generate before training. And then we update the parameters of this LLM so that it becomes more likely to generate better responses and also less likely to generate worse responses. So that's the idea of training. Basically, we are just trying to continue training this LLM. So instead of applying self-consistency, the model becomes more capable to just generate the best response in its first attempt. Still, we can combine it with self-consistency. It's not going to fully replace it. But basically, the intuition is that we want to make this self-consistency work at the training time and train the model so that we end up with a model that can generate the best response in the first attempt. So that's the idea. And we saw how this process works in the previous lectures. Basically, this visualization is coming from the post-training part of LLMs in week 1. And still, we can follow the same, very similar idea to continue training our LLM with chain of thought intermediate steps. Basically, still, we have the same model. How should I learn ML? We get this LLM. The LLM have multiple rollouts, meaning that it has multiple generations for this same prompt. And we have a reward model. We'll talk about how to build this reward model. But let's assume we have a reward model that can score these generations. So the reward model score each of them. For instance, the first generation is scored 0.26. The next one is 0.13 and so on. And then we use some reinforcement learning algorithm like PPO to update the parameters of the LLM based on these scores and the prompts, such that for the same prompt, the LLM becomes more likely to, for instance, produce this response, the third response, because it has a highest, or maybe fourth response, because it has the highest score, it's 0.95. And also it becomes less likely to generate this response because it has a very low score. So there is this loop. We continue this loop with multiple iterations and multiple updates to the parameters happen. And then after it's over, basically we end up with a fine-tuned LLM, which can generate responses that are typically going to be scored higher by this reward model. So now the main question to answer is this reward model. How are we going to really build this? And there are two ways we can build the reward model so we can continue training our LLM with chain of thought capability. One approach is ORM, or Outcome Supervised Reward Model. And the second approach we'll talk about shortly is PRM, or Process Supervised Reward Model. So let's start with ORM and focus on that. Basically, we want to train a reward model. And then the data that we have is in this format. We have prompt, we have some intermediate steps which are generated by the LLM, and also we have the final answer, also generated by the LLM after its intermediate steps. So these are already available to us. We can easily use our LLM to generate such outputs for different prompts. And then we need to also label this. The label is basically saying that how accurate or how good the final answer is. For example, in this case, if it's accurate, let's say in a mathematical question, we have the prompt, we have some ground truth from our data set. So we already know the correct answer. So when we pass this prompt to our LLM, we get this generation, chain of thought, and final answer. We can parse this output, look at its final answer, and then label it, meaning that if the final answer is equal to the correct answer, we label this kind of generation, we score it 1. Otherwise, we score it 0. And by we, I'm talking about the real humans and annotators that are responsible for building our data set to train this model. And there are different ways we can collect this. Again, in certain domains like mathematical questions, we have access to data sets with prompt and their correct answer. Also, it's easy to prompt the LLM with to follow a certain format so that we can easily parse the final answer and compare it with the ground truth. So in certain domains, we can automatically label our data. And those tasks we saw that they are called verifiable tasks, meaning that we can easily verify the output. So we can, while we are creating the data, we can basically label it automatically. There are other ways also, especially in different domains, which are more difficult to automatically label them. For example, let's say in writing, creative writing. In those cases, we can rely on user feedback in the UI, for instance, or we can hire experts and annotators to look at these, go over all of this, and then look at the final writing or whatever, and then score it. So that's all we need for data preparation. We can easily generate this using the LLM, and then we can label the final answer automatically if it's verifiable task, or using real humans if it's not verifiable task. Now we have this data. Now it's time to train. And again, our input is basically the question or the prompt, a sequence of thoughts or these intermediate steps, and the final answer. And the label is basically the score that we assigned to each of these inputs. And the loss we can apply is, again, it's a standard cross-entropy loss on the final score. And it's very standard for classification task. So we'll have this reward model. This input as a whole goes into the reward model. The model predicts some score. And then we apply the loss, cross-entropy loss, between the predicted score and the label or the true score, which we have here. And we just continue training this reward model on different inputs. So at some point, the reward model would be a good estimator of what humans would would perceive the final answer if it's unverifiable task. If it's verifiable task, the reward model would be a good estimator of how accurate the final answer is. So that's how we can train the reward model. And again, this reward model can be just a copy, like its architecture is usually can be similar to LLM with minor modifications. So a lot of times we can just copy our LLM and use it as a reward model, make certain modifications to it so that its final output is a score instead of the token probabilities. And then just train it. So this is how really reward models can be built in terms of its architecture. And beside that, everything else is pretty similar, like in terms of training. We have this data, we pass it, we get the output, we apply the loss, compare it with the true label, and then the optimizer would update the parameters of the reward model so that next time for the same input, it can predict the score, which is closer to the true score or label. So this is ORM, but it has a major limitation. And its limitation is that it's only look at the final answer. Basically, this is how we are collecting our data. We are labeling our data. We are labeling only based on the final answer. So after training, we would end up with a reward model that would only predict a score that reflects the quality of the final answer. So it's not really looking at any of these intermediate steps or thoughts. So even if at some point here, there is some incorrect thought or vague thought, the reward model would just discard those. It has no idea about those. And again, that's simply because this is how we constructed our data. We are just labeling the final answer. The model may learn some correlations by just looking at them and learns that, when this certain pattern or this certain correlation exists in the thoughts, the final answer is correct or incorrect. So very implicitly, it may has some idea about correct versus incorrect thoughts. But again, it's not explicit. The model really is not going to look at each of these and figuring out if this is a right reasoning or right next step or not. And so that's the main motivation for processed supervised reward models, or PRMs. Basically, OpenAI published this paper in 23, and it's called Let's Verify Step by Step. And they're proposing to switch from ORM to PRM. And again, the paper is very detailed and interesting to take a look. And they're talking about how they're collecting their data to train this PRM model and so on. But again, the high-level idea is that instead of scoring or labeling the final answer, during the data collection process, we score each intermediate step as well. And then when we are training the reward model, we also train it such that it can predict these intermediate scores as well. So basically, the training data, the input would be the same question, a sequence of thoughts. And then the label would be, and this answer is basically referring to the final answer. It's still part of the generation. And the label is basically the human scores for every single thought here, including the final answer. And then we'll use the same cross-entropy loss, same architecture. We can start from some decoder-only transformer and just make minor modifications to it so that its final output is basically just numbers. But basically now this reward model would output a score for each step. For a step 1, it would output 1 score, a step 2 a score, and a step n a score. And then during the training process, we use the cross-entropy loss to optimize these scores, and by comparing them with the true score or the labeled scores. And this way, the optimizer keep updating the parameters of the reward model so that next time it predicts scores for each step that are closer to the true scores. So this is great because now PRMs are has better idea and can have a better overview of each step in the chain of thought process. So they are more capable and they can be more useful. But the main problem is that the generation of these scores cannot be automatic, even for verifiable tasks. So the paper is suggesting certain ways, and but again, the TLDR is that it's not possible to scale in a reliable way to automatically score our data set, score all the intermediate steps. And then there are some other papers published by DeepMind, I think. It should be this one. And it's an amazing paper. It goes over PRM, and what they're trying to do is they're trying to propose a solution so that they can automatically scale and collect their data and label all those intermediate steps. And they are suggesting something like Monte Carlo tree search algorithm, and they are basically forming this tree, and then based on this tree, they try to score each intermediate steps. I'm not going to go into the details. It's very detailed. If you're interested, you can take a look at the paper. But just wanted to say that there are some efforts later after the OpenAI's paper to automate this process so that they can, in practice, employ PRM. So that's about it. That's reward model training, how to train the reward model. And this is the screenshot from the OpenAI's paper. Let's verify step by step. As you can see, for this question, there are these intermediate steps. And then the annotators are asked to score them. And in their case, there are just 3 categories of scores. If the intermediate step is in the right direction and correct, it's this happy face. So they score it. They click on this. Again, if it's incorrect, they click on this. I think this was referring to if the intermediate step is not useful or it's a little bit vague, but I'm not sure. You can take a look at the paper. But again, they have 3 categories when they are collecting their scores. And in general, we can come up with something to convert them into numbers. For example, we can say this is numbered 1 or score 1. We can replace this with the score 0, and this can be a score 0.5. So when we are training our reward model, the reward model would try to predict those scores. All right, that's all I wanted to share for this second way of improving the LLM with reasoning capability. Basically, a quick recap is we start from an LLM which is trained for chain of thought. Again, that was here. we train with COT data, we get a new LLM. Now this LLM, we can apply reinforcement learning with some reward model to improve it so that it generally generate chain of thought answers that are more accurate. And then we saw that we can use two different reward models, ORM or PRM. Of course, PRM would lead to better overall LLM after applying this reinforcement learning algorithm. But the problem is that it's not scalable to label them or create data for it. And then we saw some other papers by DeepMind that try to automate this process. But before I wrap up this technique, one more thing I want to share is that this PRM, it's very powerful technique. So if we have a reward model based on PRM, it has two use cases. One use case we already saw, we can use it to continue training or fine-tuning our LLM to make it so that the LLM can practice and can generate responses that would be scored higher based on this reward model. But it has also a second use case, which is also very important. And it can be used at inference time. If we have a really great PRM model, we can use that model to run search. So we saw at, so here, at inference time scaling, we saw that there are different methods for generation and decoding. And we saw that at some point, it's basically converging into a search problem. Basically, the idea is to search, form a tree, and search over it to find the best sequence of thoughts that lead to the best final answer. If we have a PRM model, basically, easily we can figure out which thoughts or which directions are good, and we can stop continuing the directions that are not good. For example, at any given point here, we can just pass this sequence of thoughts to our PRM. We see what is the score of this thought. And if it's not too good, we just stop exploring this direction. And also, similarly for good directions, we just pass it to the PRM. If the PRM predicts a very high score for this step, we continue exploring this direction. So again, PRMs and in general reward models, but PRMs in particular that score each intermediate steps can be very powerful so that we can search against them at inference time. So that's another use case of PRMs and why they are very powerful in practice. And I believe most of the reasoning models, most of the advanced chatbots are using some version of internal reward models or verifiers so that they can perform search at inference time. All right, so let's just wrap this up and then switch to the next technique. So the next technique is self-correction. We also saw, again, something equivalent of it at inference time. We would talk about that. But let's first understand what is the current issue. So again, a quick summary. When there is no reasoning-related training and we use the LLM, we pass the prompt, the LLM would produce the final answer. And it's not ideal because the final answer, the LLM may have to internally think for certain tasks and break it into intermediate steps. So for many tasks, mathematical questions, this would fail. And that's why in the first place, we started to train these models capable of, to have capability to do reasoning. Then we saw COT training. With COT training, when we pass the prompt, the model would learn to generate this sequence of intermediate thoughts followed by the final answer. So this way, the model is more capable to answer more complex questions which require intermediate steps or reasoning. Then we saw reinforcement learning using reward model such as ORM, PRM. And basically the idea there was that, okay, now we have this COT, LLM trained with COT, which is great, but how can we improve it so that it generates the sequence of thoughts and final answer that is more likely to be correct in its first attempt. And then after that, we came up with this LLM, which is fine-tuned with reinforcement learning, which we know that it's more likely to generate better sequence of thoughts. But now the problem is still something may go wrong during this process. Still we have an LLM, but at some point, if one of the intermediate thoughts is incorrect, it's very likely that the future thoughts would be also incorrect. And as a result, the final result would be incorrect. So how can we fix that? This is the problem that we want to fix it. And that's what what is the purpose of correction? Basically, we want a method or use some algorithm such that even when LLM makes some mistakes and generates some incorrect final answer, it can correct itself. And we saw something similar on ChatGPT reasoning models. When we enter a prompt, as it's thinking, it may explore different ideas, but at some point it may realize that those ideas are not correct and it's not good direction. And then it may backtrack or start thinking in a different direction or self-correct itself. So more formally, basically in self-correction, the LLM detects and revises its own responses in order to eventually get to a better final response. And when we talk about self-correction, it's somewhat equivalent of sequential revision, because in order for a model to self-correct itself, it has to first produce something so that if it's incorrect or not optimal, then it can correct it. So in most of the cases and papers where they talk about self-correction, it's some sort of sequential revision is involved. And this is the visual. Without self-correction, the LLM, prompt LLM, we have this one single COT output. Now with self-reflection, we want to have something like this. Basically, the LLM generates one COT output, and then from there, it tries to improve it if it's incorrect. And then again, it tries to improve the output too. And then this becomes, let's say, the final answer. All right, so how can we really add self-correction to our model? There are two ways we can do this. One is at inference compute, by spending more compute or tokens at inference time. And the main approach for that is just prompt engineering. We saw that earlier. I would show you in a bit. And then the other way is to use training compute. And we basically train a model for better revisions. So we'll shortly review these two methods. But another aspect of self-correction which is very important, is whether the presence of external feedback. Or in other words, is there a reward model or verifier available to us or not? And because of this question, there are two ways of self-correction usually you would see in papers. One is intrinsic self-correction. In intrinsic self-correction, basically the idea is how can we train a model so that it can correct its initial response without any external feedback. The second self-correction approach is extrinsic self-correction. And basically, these are the models that are capable of correcting their response using some external feedback. So we'll go over all different combinations. We'll go over inference time compute with intrinsic self-correction and also with extrinsic self-correction. And then we'll switch to the training compute approach. So for the inference compute, in order to spend inference compute to make self-correction possible, the main approach is prompt engineering. For example, we pass the prompt to the LLM, and then the output is, let's say, COT output 1. And then we pass this along with some additional prompts, let's say, evaluate and fix errors, if any, to the LLM, to the same LLM. Basically, we make another LLM call. And then the LLM basically outputs this COT output 2. Again, we do exactly the same thing, evaluate and fix errors, if any. And then finally, we get the COT output 3. So remember, again, this LLM is it's not trained for revision. It's just the original LLM, perhaps capable of doing chain of thought, or also having been trained with reinforcement learning to have better chain of thoughts, but it's not trained for revisions. Therefore, we are just using some inference time trick, prompt engineering, to make it revise its answers. And then for intrinsic, basically the assumption is that we have no access to external feedback or reward models. So we really don't know which of these responses, output 1, output 2, or output 3, is good. But since it's sequential and we believe that each step, it's basically fixing some errors if there are, this final output 3, basically this COT output 3 can be considered the final answer. Just because, let's say we want to have an intrinsic model to self-correct itself. Now, its extrinsic version is also very similar with just minor difference. Again, same prompt goes into the same LLM, same set of prompt engineering we perform. We just pass this to output 1. Again, we generate output 2 and COT output 3. But now, in order to pick the response, we are not by default going to pick the final output. We are going to now use our reward model because, again, it's extrinsic. So we are assuming that we have access to some external feedback, such as a verifier reward model, or it can be some heuristics. For example, if it's I don't know, like if it's a coding question, we can just run it and see if it leads to any error or not. But again, no matter how we want to do it, we get some external feedback, let's say using some reward model. Now we use this reward model to score each of these outputs. And then if this output has the highest score, we would pick it as the final answer to show to the user. So this is the self-correction mechanism, both extrinsic and intrinsic, at inference time, or if you are using inference compute. And we already saw this. Again, here in the previous videos, we've saw this sequential sampling, or sometimes it's called sequential revisions in paper. And we are just spending inference time. These models are not trained to do revision. We are spending inference time and use prompts to push it to do that. Now let's switch to the training compute, which is the main purpose of this video. How can we really train the LLM for better revisions? And the idea is very simple, like very similar to training with COT data or training with reward model. In order to train for better revisions, we just collect the data, we collect revision data, and just fine-tune the LLM on it using the exact similar training process. So revision data is basically in the form of trajectories. It typically has a sequence of incorrect answers followed by a correct answer. So that's basically the data that we want to collect and name it revision data. And we show it to the model so it learns from it. It learns that, all right, after some sequence of incorrect answers, we have this correct answer. So the model would learn from it so that whenever it generates an incorrect answer, it can fix it or correct it with a correct answer. And there are two ways for doing that. There is this, we can just do SFT or supervised fine-tuning for self-correction. And basically here the idea is just to pass the LLM with this revision data we collected and continue training it. So iteratively it just learns to revise its answers. And this paper is basically discussing some details about following this approach. The other approach is we use reinforcement learning for self-correction. And that's this paper here, Training Language Models to Self-Correct via Reinforcement Learning, published by DeepMind again, late 24. And basically this method is saying that SFT is not good. SFT for self-reflection is not really better than just doing self-consistency. Basically, you can read the paper, go through the details. It's saying that other methods for intrinsic self-corrections is not necessarily better than self-consistency or just sampling in parallel and picking the best response. And then they are proposing a solution to use reinforcement learning with very careful terms for penalizing the process to make self-correction works. Again, I'm not intending to go into the details. It can become very technical. You can read it if you are interested. But I've already shared at high level what they are trying to do. They are trying to use reinforcement learning so that the model can self-correct itself without any external feedback. And the approach called the score. So again, this is just what I mentioned. They shared that previous approaches do not work, including SFT for self-correction. And then they are training the model in a very unique way using reinforcement learning to make revision better. And basically, after training, the model becomes very good at revising itself. So the question is now, after training, how are we going to use this model, this fine-tuned model with the score method? Basically, it's still very similar to what we saw at inference compute approach for self-revision. The workflow is exactly the same. The main difference is that now this LLM is more capable. So still we pass the prompt to the LLM, we get the output 1, we use certain prompt, which we also saw in this diagram here, optional external input. We can pass it to this LLM, we get output 2 and output 3. But by default, we can assume that, again, since it's intrinsic, we can assume that output 3 is the final answer. But now the main difference of this LLM versus the one that we saw at here for inference-only compute spending is that this model is trained to revise itself. So it's usually doing better. So whenever we pass some output to it that is incorrect, it's generally better at identifying that and fixing that because this is how it's trained. And that's it. That's about self-correction. One more thing I want to share is that we can also provide these LLMs not only with these fixed prompts, but also with some external feedback if it's available. Again, in terms of intrinsic self-correction, it's not available. But in general, in practice, companies do have PRM, ORM reward models. They can use them to score thoughts or outputs. They have also access to certain tools because, again, a lot of times these outputs may have tool calling ability. So they may ask for calling certain tools, such as code interpreter. And then when we run it in the code interpreter or when we call some functions, we have some outputs by default from the function. It can be some logs, or if there is a coding, it may just fail and there are some bugs. So there is some logs in the output, and those can be also included as the input for the next revision. Again, what I'm talking about is in extrinsic self-correction, not intrinsic. But extrinsic is usually, it's reasonable to assume that we have that because companies have PRM, ORM models in general. And it can be very valuable to include the feedback that we are getting to these LLMs as well, not only a fixed prompt. So that's it. That's all about self-correction. And yeah, the next technique that we are going to now switch to is how to internalize search in this reasoning process. What does it mean to internalize search? And that's, again, the fifth approach. The intuition is that there's simple problems and we can solve those problems with less effort. And we generally know the correct solution from the beginning. For example, if you ask a simple math questions from somebody, they know what is the solution. They just need to come up with those intermediate steps followed by the final answer. However, for complex problems, there is a different scenario. If you ask somebody a very complex mathematical question, we may not know the right direction from the beginning. We may want to try different methods, and we may even end up with some incorrect directions, and we learn from them. And some of them we realize that has better potential to lead to the correct solution. So we continue those thoughts. And basically, we keep continuing different methods until we reach a solution. And basically, the idea of internalizing search is to continue training the model capable of searching, very similar to how humans would think. They think, they try different ideas. If they look wrong, they can backtrack, continue different ideas, and so on. So there was this very popular paper named Meta COT, or Meta Chain of Thought. And basically, the paper is discussing exactly similar thing. It's saying that System 2 reasoning is different from System 1. System 1, I think, is referring to the simple questions. And for System 2, basically refers to complex questions, which require more attention and trying different methods. And then it's saying that for simple questions, the answer can be just a sequence of thoughts followed by the final answer. But for the complex questions, the answer is not necessarily just a sequence of thoughts followed by the final answer. It might be starting with some solution. At some point, we may realize it's not correct, switch to a different solution. And again, we realize this is not good. We backtrack, follow a different path. And at some point, we realize that this is a good solution. And then we continue it with chain of thought or intermediate reasoning until we get to the final answer. So, and they're calling it meta chain of thought. They're saying that we have to change our data set. Instead of having a simple chain of thought followed by the question and train the model on those chain of thought data, why not we collect different data which has a sequence of chain of thoughts. Remember, each of these Z1, Z2 by themselves is a sequence of thoughts. And then basically, this setup is saying that we have to collect data such that after the question, there is a chain of thought, which is not necessarily okay or correct, another chain of thought, and all the way to the kth chain of thought. And finally, we have the correct final chain of thought solution, which has its own intermediate steps followed by the final answer. And they're calling these Z1, Z2, ZK latent thoughts, meaning that they're just the process of thinking. So that's mostly what the paper is proposing. And they're saying that if we train the model on such data, it would learn to think and try different methods or different directions, backtrack, continue other thoughts until it reaches the final solution. So the most difficult part is the data preparation part. And again, we're not going to go into the details because there are a lot of details, but if we can use some LLMs to generate such data and we use it to train the model would be capable of thinking and searching and backtracking. So again, for complex problems, we would have a sequence of data with more latent thoughts. And naturally, for simpler questions, we would have examples with less latent thoughts. And then we can follow this method. We can use inference time compute to sample various solutions from the LLM. Then we can use them to generate some initial data set. And then we can follow the same paradigm that a star paper was using to bootstrap the model iteratively. Basically, we train the model on our initial data set. We make it better. Again, we sample more solutions from it. We generate a better data set. We continue training the model on this new data set, and so on. And again, training is identical to COT or normal LLM training. Once we have this data, it becomes our new text that the model is expected to learn its distribution and predict it. So that's meta COT. And again, if we go to ChatGPT and select its reasoning models, and we ask some question, we would see that the model during its thinking process, it has basically those latent thoughts. It starts some thinking, at some point it backtracks, it tries different ideas, and so on. For example, let me write, can you figure out what are the most difficult questions in International Mathematical Olympiad, IMO, and share why you believe it is the most difficult. So I don't care about the answer. I just want to show the thinking process of this model. Let me enter this. So first we see this thinking. And probably after a while now we would see some actual latent thoughts. And see here it says the user wants to know the hardest problem. I'm going to search for posts or research papers that rank the hardest IMO problems. After this, it may search the web and try to collect more information. And again, it may think, it may change its strategy, it may backtrack. And finally, after all those latent thoughts are over, it would come up with the final output, which is the actual questions and why it believes they are most difficult. So here it says, I want to choose a set of widely regarded, and again, it's searching. So putting this function calling and searching aside, everything else that we see is basically those latent thoughts that it's trying to search over all possible directions and possibilities in the output space. And okay, here again, it says it seems like opening the site may be tricky. Okay, again, you get the high level idea. I just wanted to show that how ChatGPT is doing it in its reasoning model. They perhaps have something like similar to this. Not, I don't know what they're doing. It may not be meta COT, but they have some mechanism to train their model to internalize search, so that the model by itself, it knows how to explore different directions and come up with a solution. I think this paper also has some nice visuals of showing how this thinking and backtracking works. Again, this is meta COT paper. And they're saying that basically after we train this, the model is basically showing some kind of search and backtracking signs. So for this algorithm, for example, they have, basically they are experimenting with different ways of training this model, different ways of collecting their data. And in many cases, they are trying to have their data in such a way that some backtracking is also involved. So they search, backtrack, search again. So I think, yeah, that was the visual I wanted to show. Okay, and here, basically, they are also evaluating existing models such as OpenAI's O1, DeepSeek R1, and Gemini 2 thinking model. And they're saying that these are some of the solutions. This is basically the output for this question. And then if I zoom in, they are identifying certain backtracking efforts, which also verifies that this internalizing search is perhaps what most these models are using to train their model. So here they have some solutions, and then our equation here, let me define this. And at this point, the model says, but we can consider this. So basically, it's trying to use some previously generated tokens here and backtrack to here. And again, it comes here. So this pattern is happening both for O1 and DeepSeek R1. Here, DeepSeek says, wait, actually, since this is mining of degree 2n, the leading term. So again, it's relying on some previous information to make more logical steps. So yeah, that's the visual I wanted to show, and some more examples. This is just very interesting to read. And that's about internalizing search. There are lots of details how to collect the data, but the most difficult part is collecting the data. Once the data is collected, the training is almost identical. And another interesting observation before I wrap up this final technique is that just because during the data collection process, we have less latent thoughts for simpler questions and more latent thoughts for complex questions, the model would learn it that way. So what that means is that at inference time, when we ask a simple question, the model would not really explore lots of different questions or search for a long time. Everything would be short because this is just how it learned it from the training data set. For simpler questions, there are less latent thoughts, so the model can faster come up with its final COT answer. And for complex questions, again, according to the collected data set, the model knows to perform more search, extensive search, try all different sorts of ideas, more backtracking, and generating the final answer. So that, and OpenAI is also doing something similar. In fact, this paper, the same paper, Meta COT, is evaluating OpenAI, and they're saying that for difficult questions, OpenAI is spending more time at inference time to searching and figuring out. And for simpler questions, they are spending less time, which can also validate the idea of internalizing search in their model. So that's it. That's the final way that we can make our model to perform search and thinking and complex reasoning. And we learned all of this. One final thing I want to share is that all this can be combined again. We don't have to only internalize search and just stop there. For example, for the same question that I asked here, you saw initially the model, it was showing thinking, but it was not showing anything. It was just saying thinking. So that part is probably when the model is running some search at inference time against some verifier to figure out which direction or which set of directions has the highest potential. And once those directions are determined, then we started seeing the actual thoughts and latent thoughts and reasoning traces. And that's when basically now the model, the O3 is using its model to generate thoughts, and searching over all possible solutions. And behind the scenes, the algorithm can also employ other methods for scaling inference time. For example, it can have self-consistency, so it explores different ideas in the beginning. And by the way, here it thought for 3 minutes and 32 seconds. And lots of searches and thinking and intermediate latent thoughts. And then finally, here we see the final COT output. And basically it says below is a short list, and these are some of the questions, and here is what makes these particular problems so hard, and then some takeaway. So that's it. Let's wrap up the reasoning topic, and we switch to a feature like deep research, and we'll briefly see how deep research is relying on reasoning models to provide a very detailed report on different topics. All right, so let's understand deep research a little bit and see how they're really built in practice. In previous lectures, we saw multi-step agents, and we also saw multi-agent systems. And then we mentioned that deep research is a popular use case. And in those systems, we saw that there is this agent here, and it's communicating with an LLM and also some tools. And then in the prompt, we are using prompt engineering technique to set up this agent such that when it's sending some request to the LLM, it pushes the LLM to think. Basically, what we shared previously was more on, and also what we shared in frameworks like React, it's more like on prompt engineering mechanisms. It's more prompt-based. Now, in practice, after the reasoning models, we can easily switch from the traditional LLM to thinking or reasoning LLM. And this way, we can just get rid of unnecessary prompt engineering work. So the agent doesn't have to worry about whether the LLM would think or reason or not, because by default, the LLM is capable of thinking or even searching and backtracking. So that's how deep research tools are built in practice. They're not using a normal LLM, and they're not using React to prompt those LLMs for thinking or chain of thought request. But in practice, the LLM itself knows how to think and reason. And again, deep research was introduced first by, I think, OpenAI, and it was released in February, or it was around that date. Basically, they're defining it as a new agentic capability that conducts multi-step research on the internet for complex tasks. It accomplishes in tens of minutes of what would take a human many hours. So they're explaining why it's needed. They're not saying how they're building it in detail, but they're just describing the feature. And then there are some updates here, and I just realized that their final update, July 17th, basically they're giving the deep research feature access to visual browser as well as part of their ChatGPT agent. So now it's even more capable because now it has access to a browser and can visually go to a browser, search it, extract information, and use them as part of its data collection process. So, and also to see that in practice, this is ChatGPT UI, and basically we can select deep research. Yes, basically we can select deep research, and then we can get a detailed report about something. A lot of times it first gets back to us with some clarifying questions, and then once it knows all those clarifying questions, it has the answer for them, it would just go and start its agentic process. So let me enter something. We would not wait for it because it takes very long, typically tens of minutes. And I'll share later its output, its report, in case you are interested to see. So I can ask something like, can you create a detailed summary of every technique for training, thinking, and reasoning models, something like this. So now it may ask us some clarifying questions to help you best. Could you clarify what you mean by thinking and reasoning models. Are you referring to AI models like LLMs, cognitive? Yes, LLMs and different techniques, state of the art, which makes them to think, reason, internalize, search, and applies inference time scaling to search against verifiers and all other similar techniques. Apologies for my misspelling. I know but open the model understands them. So here it says, got it, I'll prepare a detailed summary, and then it's starting researching. And then here, if we click, we would see the activity and all the sources. So again, I'm not going to wait. It's going to take very long, but I would include whatever the output is as part of the lecture. So that's deep research tool, and that's it. And one more thing, in practice, we saw that deep research is not a multi-step agent. It's multi-agent. So in practice, the system looks like this. Prompt comes, it goes to a prompt rewriter. Internally, we are not seeing it. The prompt rewriter fixes some of the grammar issues or misspelling and so on. And then this would go to a manager agent. And manager agent would simultaneously run multiple web search agents. And basically, each of these are having access to tools, a thinking LLM and memory, and perform the search on the web. And then once they all are done, the manager agent would summarize their gathered information and come up with a final report and share it with the user. So yeah, that's reasoning models, thinking models, and application like deep research. We would see many examples in the project of different ways to use inference time scaling. And also we'll see a real example to build something like deep research, but a lot simpler.